Welcome back to Hansen theory. Until now, you learned about molecular forces. You learned about Hansen space. You learned that compatibility is a distance problem. Today, we turn that idea into something engineers can actually use. Because visualization without quantification is incomplete. And numbers without understanding are dangerous. RA distance and red number exist to bridge this gap. They convert molecular geometry into formulation decisions. Let's begin with a reality check. Most formulation failures do not happen because engineers lack data. They happen because engineers do not know how to interpret relationships between materials. They see resin data sheets. They see solvent properties. They see compatibility charts. But they do not see interaction distance. Hansen theory introduces a simple but powerful concept. If two materials are close together in Hansen space, they are more likely to be compatible. If they are far apart, they are more likely to fail. RA is the mathematical representation of this separation. RA is not just a formula. It is a measurement of interaction mismatch. It tells you how far the solvent's force profile is from the polymer's force profile. When RA is small, molecular interactions align. When RA is large, forces fight each other. This is why two solvents with similar boiling points can behave completely differently. Because boiling point does not measure interaction distance. RA does. Now, let's talk about what most engineers miss. RA is not measured in physical millimeters. It is measured in interaction energy space. This means it represents difference in force balance, not physical size. You are measuring how much correction your solvent system needs to match the polymer environment. Now comes the second concept. Red number. Red is simply RA normalized by the polymer's tolerance radius. But this simple ratio carries massive engineering value. It answers one question clearly. Is this solvent system inside or outside the polymer's compatibility zone? When red is less than 1, the solvent falls inside the solubility sphere. This means compatibility is likely. When red is close to 1, the system is borderline. This is where partial solubility, sensitivity, and instability appear. When red is greater than 1, the solvent is outside the sphere. Failure becomes predictable. Now here is where minority thinking begins. Most engineers treat red values as pass or fail indicators. They see a number below 1 and assume success is guaranteed. They see a number above 1 and assume nothing can be done. This is shallow thinking. Red does not replace engineering judgment. It supports it. A red value of 0.9 and a red value of 0.2 are both technically inside the sphere. But their behavior will not be the same. One is close to the edge. One is near the center. This difference matters. Systems near the edge are sensitive to temperature changes. They are sensitive to solvent evaporation. They are sensitive to raw material variation. Systems near the center are robust. They tolerate processing variation. They survive scale-up. This is why experienced formulators do not aim for minimum acceptable compatibility. They aim for stability margin. Now, let's talk about solvent blending. When you blend solvents, you are adjusting RA in real time. Every component you add moves the blend's position inside Hansen space. You are not mixing liquids. You are tuning interaction coordinates. By adjusting ratios, you can pull the blend closer to the polymer center. This is engineering control, not guesswork. This is why blindly copying solvent recipes often fails. Because the same ratios behave differently with different resin grades. Now consider pigment dispersion. Pigments do not dissolve. They interact with resins and dispersants at the surface level. If your resin system sits far from the pigment surface energy zone, dispersion stability suffers. RA distance helps you understand why wetting agents sometimes work and sometimes fail. Now, let's address a dangerous industry habit. Many engineers use software to calculate RA and red values without understanding assumptions. They trust output numbers blindly. But Hansen parameters are experimentally derived averages. They are not absolute constants. Temperature shifts them. Molecular weight changes them. Additive presence alters them. This means RA and red values are guides, not laws. Senior engineers use them as directional tools. Junior engineers treat them as rules. This difference defines professional maturity. Now here is the most important insight of this episode. RA and RED are not about prediction only. They are about diagnosis. When a formulation fails, you should not ask, which ingredient is wrong? You should ask, which interaction balance moved outside the compatibility zone? This reframes troubleshooting. Instead of random adjustments, you apply targeted corrections. You change solvent polarity. You adjust hydrogen bonding contribution. You modify dispersion balance. This is controlled problem solving. Now, let's connect this to production reality. Scale-up problems often happen because solvent evaporation rates change. As volatile solvents leave the system, the remaining blend shifts inside Hansen Space. RA increases. RED crosses critical thresholds. Suddenly, a stable lab formulation becomes unstable in production. Engineers who understand this can design evaporation balance blends. Engineers who don't will chase symptoms endlessly. This is why Hansen theory is not academic decoration. It is a production stability tool. In the next episode, we will move deeper into polymer behavior. We will explore why polymers behave differently than small molecules. Why molecular weight matters. Why swelling is not the same as dissolution. If you want to understand resin behavior instead of memorizing compatibility charts, stay with this series. This is Hansen theory.